Okay, thank you all for uh, joining to this meeting. Today I'm going to give you a brief summary of my PhD project that I did since 2017, which is entitled A Single Step and GPU Accelerated Simplified Lattice Boltzmann Method for High Turbulent Flows on Complex Domains. So first, I'm going to give you an introduction of the context of the project, followed by a theoretical background of the computational fluid dynamics model that I've been using, which is the Lattice Boltzmann method. And then I'm going to talk about an implementation in GPU of the latest simplified Lattice Boltzmann method, and an improvement on the methodology known as the single step and simplified Lattice Boltzmann method for high turbulent flow, and followed by the GPU acceleration of this proposed model. And finally, versatility expansion of the model for the simulation of irregular fluid domains. And in the end, I'm going to talk about the potential developments and the future work. So in mid-2016, I was working with Tecnológico de Monterrey in the wind energy group, developing an aeroelastic model for the design and optimization of wind turbine rotors, which is a project that is subdivided in two subtopics, which is the topology generation and also aeroelastic modeling. So in the beginning, we were focusing on developing low computational cost models for the structural and aerodynamic model. The structural model is based on the thin wall beam model from my supervisor, Diego Cárdenas, and I coupled it with the blade element momentum theory for the aerodynamic model. So we started developing this interactive tool for generation of the wind turbine blades, the topology. Luckily, we published this article in 2019, and the tool is able to assign as well the material properties of the surface of the blade, and you can also couple this this tool with the numerical model that my supervisor did in his PhD, which is the thin wall beam model. So you can compute the displacements and stresses of the surface of the blade. On the other hand, I was developing as well the implementation of the aerodynamic model based on the blade element momentum theory in this interactive tool, so you can manipulate interactively the operation of the rotor. But I found out that there are some limitations on the model. Excuse me. So basically, this model is defined by empirical models, and it has a lot of limitations because it has a lot of correction models to model the phenomena that is around the rotor, such as the shadow of the tower and the recirculations behind the rotor. So I decided to explore alternatives to solve this problem. So I focused my project to do a high fidelity CFD model. So just to give you a very brief summary of the state-of-the-art exploration, commonly you can use the Navier-Stokes equation to develop the computational fluid dynamics models. Typically, there are different flavors, such as the direct numerical simulation, that is a high fidelity that can capture all the complexity of the flow. And there are some high mid-fidelity and mid-fidelity models, such as the large eddy simulation and the Reynolds average Navier-Stokes equation. But on the other hand, I found an alternative model, which is the Lattice Boltzmann method, which is as well a high fidelity model. And this relatively new CFD model based on the Boltzmann transport equation. The advantages of this model is that it's a fast CFD model and it's highly parallelizable, and it captures all the complexity of the flow and doesn't rely on the solution of linear systems. But one disadvantage is that it's limited to low Reynolds numbers. So this is something that we have to overcome if we select this model. And the objective of the PhD, in a nutshell, is to develop an accurate high fidelity CFD solver based on the Lattice Boltzmann method, specifically the simplified Lattice Boltzmann method, and accelerated for the first time with GPU technologies for real-time and interactive simulations, and to improve the algorithm to allow the simulator to conduct simulations with high turbulent flows. So a brief summary of the theoretical background of the Lattice-Boltzmann method. The conventional Lattice-Boltzmann method, it's based on the kinetic theory of gases. So as you know, you can define the fluid in different scales, such as the macroscopic scale, where you can define the fluid by the density and the velocity of the flow. And in the mesoscopic scale, you can define the fluid statistically with the probabilistic distribution function, or PDF. This PDF gives you the probability to find a specific set of particles in a specific location with a specific velocity in a specific time. The evolution of this PDF is defined by the Boltzmann transport equation, which is basically a simple differential equation that has two operators, an advective operator and a collision operator. So if you discretize or decompose the velocity space in finite velocity components, such as in this model that has 9 components, you can approximate the Boltzmann transport equation with this expression, and the collision operator can be approximated by a simple difference between the PDF components and their equilibrium state components, multiplied by a factor that is commonly known as the relaxation time factor, which is highly related to the viscosity of the fluid. So the equilibrium PDF in this term can be computed with the macroscopic flow variables that I mentioned before, the density and the velocity field. This is something that I want you to remember, that this equilibrium PDF can be computed with the macroscopic variables. So to recover the macroscopic variables, you can also do numerical integrations of the PDF components to obtain the density and the momentum, and ergo the velocity field. And finally, if you know a previous time step of the distribution function components, you can compute the future time step of this PDF, and then you can compute the macroscopic flow variables. So this procedure is the same for each node in the fluid domain. And since you only rely on the local neighbors, you can parallelize this process. But one of the drawbacks of this process is that you have to allocate the PDF in the memory. So for example, in here you have 27 components in the 3-dimensional space. So you have to allocate that for each grid point in the fluid. So this is something that you have to eliminate somehow. And this is something that it has been solved in the simplified Lattice-Boltzmann method, or HSLBM for highly accurate simplified Lattice-Boltzmann method. This procedure is derived since 2014 by Changshu and developed by Shenchen in 2017. And the main objective is to eliminate the storage of these PDF components and only retain the macroscopic flow variables. But the model somehow, or this approach, compromises the spatial accuracy of the model. And you have to rely on a spatial interpolation to mimic somehow a virtual grid point that is finer than the original grid point. And you as well require a fractional or intermediate step, which is basically a procedure where you have an intermediate step known as the prediction step, where you compute a predicted value of the macroscopic variables, which is computed with the equilibrium PDF. So as I mentioned before, the equilibrium PDFs components, you can compute it with the macroscopic variables. And because of that, you don't have to store the PDF components. Then you do a correction and you finally get the next time step for the macroscopic variables. And as you can see as well, it only depends on the equilibrium PDF. So you only reconstruct the macroscopic flow variables and you don't have to store them. The improvements in here is the memory allocation is reduced, but the drawbacks is that you require a fractional step and you require a spatial interpolation stage to restore the spatial accuracy, which is mainly the bottleneck. So for the first step that I did in the PhD is to implement the HSLVM in GPU. The main objectives of this was to, for the first time, accelerate the process with graphical architectures and an efficient spatial interpolation to reduce the bottleneck of the algorithm. Luckily, this was published last year. And let's just dive in a little bit. The GPU acceleration is useful for highly parallelizable simulations, such as the finite difference scheme in wave equations. And it's as well useful for bidimensional and three-dimensional post-processing for biomedical studies, etc. In the context of the Lattice-Boltzmann method, you can decompose the fluid domain in multiple work items, and you can solve this simultaneously using the graphic cards architecture, because the nowadays graphic cards, even in the portable devices, they have thousands of computing cores compared to the CPU. So basically what I did is I transported the methodology of the HSLVM to GPU computing by using two kernels or two codes that are compiled in the graphic card, one for the prediction step and the other one for the correction step. But you can see here that you have two bottlenecks for the interpolation stage. So you have to somehow reduce these bottlenecks. For this, I proposed an efficient spatial interpolation stage, which is I noticed that the virtual streaming points in the finer grid are somehow aligned with a specific set of grid points in the original grid. So you can reduce the number of coefficients to interpolate a point. For example, in a three-dimensional case and in a fourth order full spatial interpolation, for the total virtual streaming points, you require 3,375 coefficients. In our case, with the directional, you only require 135 coefficients. So you have a decrease of 96%. And this should be noted in the performance of the model, and it should retain the spatial accuracy of the model. So in order to quantify this, I use the lead-driven cavity benchmark for two-dimensional case, which is basically a benchmark where you have a flow that is generated by a moving boundary in the top and creates a primary vortex inside. For this case, I used a Reynolds number range from 100 to 15,000, and this particular configuration with 384 time steps computed. And I compare with the original simplified Lattice-Boltzmann method that doesn't have the spatial interpolation, the HSLVM from 2018, which has a spatial interpolation, and as well I compare the proposed algorithm with the literature results as a reference. So just to give you an idea of this slide, you can see here the flow inside the cavity for a Reynolds of 100. In this graph, you can see the horizontal velocity component in the vertical line. And in here, you can see the vertical velocity component, as you can see in the arrows, in the horizontal line. For this case, you can see that all the simulations have the same result. It's not surprise for a Reynolds number of 100. The green line is our proposed directional interpolation. This is the full spatial interpolation, and this is without any interpolation, and this is the reference. If we increase the Reynolds number to 1,000, we can see that the non-interpolation case, it has a little bit of deviation, but our model or our interpolation stage doesn't lose the accuracy if compared with the HSLVM. If we increase even more the Reynolds number, you can see now a big deviation on the simplified Lattice-Boltzmann method, but our work is identical to the work of HSLVM. And finally, for 15,000, we can see the same story. Our directional interpolation is reproducing identically the results of the HSLVM. And so in here, you have been proven that the model it's comparable with the results of the HSLVM, but with a most or less computationally expensive interpolation stage. And how this is translated to GPU performance with the addition of the GPU acceleration. Here's where it really shines. The simulation in here that I did is I compared the HSLVM from Chen in 2018, which is derived it's a program in CPU. And you can see, for example, for the 300 per 300 grid points, it took about 4 or 3.7 hours to do 500 time steps. In our work, we did a simulation that it's conducted in only 1 minute. So it's a simulation that is 200 times faster if we compare to the original highly accurate simplified lattice Boltzmann method. So just to wrap up this section, we have a significantly better spatial interpolation. And for the first time, we did a GPU acceleration of the simplified lattice Boltzmann method, which is 200 times faster than the CPU, and it allows real-time and interactive simulations, as you can see in this animation in here, where you can move the plot in different angles. So I didn't want to stop there because there are two main bottlenecks that are still in the HSLVM. So I proposed a new implementation, and I entitled this as the single step and simplified lattice Boltzmann method for high turbulent flows. So basically the main objectives of this model is to develop a highly accurate simplified lattice Boltzmann method without any interpolation stage, and eliminate completely the fractional step. That is why it's entitled single step. And I added a turbulence model to allow the simulator to have turbulent flow, or to be able to simulate turbulent flows. Luckily, this was published this year, and it's gaining a little bit momentum. Actually, I think last week it was cited by an author that is using it with my magnetohydrodynamics, and it has been proven that it's significantly faster. It is elegant, and it's as accurate as I claim. So it's so elegant that you only depend on two main equations derived from the discrete Boltzmann transport equation, and doing a combination of Taylor series expansion and Chapman and sub-expansion truncated to the second order. You can approximate the Boltzmann transport equation with this differential equation in here. And by using a treatment that I did with conservation laws and the finite difference treatment, I was able to compute these two equations to compute the future time step for the macroscopic flow variables, which, as I told you before, it only relies on the equilibrium PDFs. So no storage of the PDF components, just only the macroscopic flow variables. I additionally added a turbulence model to eliminate the only disadvantage of the lattice Boltzmann method, which is that it's not capable of simulating high turbulent flows. So basically the large eddy simulation, what it does is that it adds a viscosity term that dissipates the vortexes that are smaller than the numerical grid. There are numerous models. For example, the most commonly used is the Smagorinsky. It's pretty simple. And then there is the whale model that it's more sophisticated and is more accurate. And there is an in-between Bremann's model that is as simple as the Smagorinsky, but it's as accurate as the whale model. So no brainer in here, I select the Bremann's model and I implemented it with my model. So let's talk about the GPU implementation of this algorithm. So as you can see here, I am using only one kernel. the single step kernel. And as you can see in here, you don't have an interpolation stage. So theoretically, because you only have one kernel, you have double the performance. But because you don't have the interpolation stage, you have to have more performance improvement. But first, let's talk about the accuracy. We did the same benchmark, the lead-driven cavity, but we expanded the Reynolds number up to 65,000 because the turbulence model allows us to have simulations that are more stable. The same configuration, but in here I only use the literature references, but I am not using any interpolation stage to compare. So for Reynolds 100, we have excellent results, no surprises in here. If we increase to 1,000, we see that we are behaving similarly to the reference as well. If we increase again to 10,000, I believe you have excellent accuracy without any interpolation stage and without the fractional step. For 30,000, we can still have excellent accuracy. We have some deviation here, but as you can notice, there is an unsteady simulation in here. So the lead-driven cavity somehow is not suitable per se for this comparison, but I still use it and I compared with some results. And finally, for a 65,000 Reynolds, you can still see that the simulation it's stable. It doesn't become unstable, and it's an unsteady flow. And we can retain the spatial accuracy. There are some deviations because these results are average, but maybe the maximum in here can touch these points on the reference. So it has been proven that the spatial accuracy is good in the two-dimensional world. If we check the three-dimensional world as well, I did a simulation of the jet flow for a Reynolds number of 184,000 with a square inlet. So you have a flow that enters in the cavity from here to the Z direction. I used 8 million grid points in this case, and I compared with numerical and experimental results. The numerical results are with the conventional lattice Boltzmann method. So we have the capability to conduct simulations with all the complexity of the flow with our model. And if we compare the magnitude, the velocity magnitude in here with the numerical and the experimental results, we can see that the decay behaves similarly to the results from the literature. Furthermore, if we check as well the evolution of the profile along these lines, you can see that the evolution is behaving as well similarly to the results from the experimental and numerical results. So the spatial accuracy has been proven to be retained, and it is compared to the conventional lattice Boltzmann method, but how it behaves performance-wise. For this, we can compare with the previous implementation, and it is 2.5 times faster. So it's more than double than the implementation from last year. And it is 540 times faster than the CPU implementation from 2018, where you can see that you don't have a visibility of the performance of the work of the Chen et al. And the penalization of the turbulence model is minimal. So just to grab this section, 540 times faster than the CPU implementation, 2.5 times faster than the 2020 GPU HSLVM that I proposed last year, no fractional step, and no interpolation stage are required. And it is able to simulate high turbulent flows and is suitable for interactive simulations as well. So again, I didn't want it to stop there, and I wanted to add a versatility expansion to allow the simulator to simulate irregular or the flow inside irregular fluid domains. So the main objective of this section is to expand the versatility and allow to simulate curve boundaries and allow local refinements. This manuscript is in progress, it's almost finished, and I wanted to publish this year. But basically, the capability now is that you can simulate a flow in a much bigger domain with refining capabilities. You can see here that the airfoil, it's in a more refined mesh, and you do a zoom in here and you see that the alignment of the cells are aligned with the profile. So here you have a domain that is 25 times the diameter. The diameter is 25 times the core length of the airfoil. But in here, I have to be honest, we require a virtual streaming step or interpolation. So this is a new bottleneck that it's out of the scope of the PhD, but it's important because of the versatility that you can gain. You have to reconstruct the parametric coordinates of the virtual streaming points, but you can compute this in a previous step before the algorithm. So basically, you define the mesh, the two-dimensional or three-dimensional curve domain. You compute the parametric coordinates of the virtual streaming points, and then you do the single-step simulation in here. But we have this interpolation stage. So this is something that I have in my mind, and I want to resolve it in the future. It's not inside this thesis. So I'm going to show you two of the benchmarks that I published in my thesis, which is the low Reynolds number and the high Reynolds number in three-dimensional case as well. So first, I did a simulation of the circle, the flow around the circular profile in a domain that is 100 times the diameter of the circular profile. And this is compared with the results from the literature from Wu et al. And Xu et al. So qualitatively speaking, we have a simulation. We are reproducing the streamlines of the results in the literature. You can see here the recirculation length compared to the recirculation length in the work of Wu, and as well as the pressure distribution computation around the circle. It's practically identical to the results from Wu et al. If we double the Reynolds number, we can see that the recirculation length it's increased similarly to the work from Wu, and we can see that we have similar results as well in the pressure distribution for this case. Quantitatively speaking, we can compute the drag coefficient, the recirculation length, and the separation angle, and we can check in the worst case scenario, we have less than 3% of the percentage error if we compare with the literature. Additionally, if we increase the Reynolds number to 1.5 million, and we use airfoil, the NACA 4412, and we have an angle of attack of 14 degrees, we can do a simulation to compare the results that are experimental from NASA, specifically from Coles et al. You can see here that we have the proper refinement of the mesh closer to the boundary. And you can see that we can compute the simulation as well. The velocity magnitude is depicted in this figure and the streamlines. And in here you can see the pressure distribution in all the fluid domain. If we check the pressure distribution from the work of NASA, or from Coles et al., you can see that we are matching the results from their work. Quantitatively speaking, we have a lift coefficient that is 1.69 for our work, 1.66 or 1.67 for the work from Coles et al., with a percentage error of 1.24%. And the drag coefficient, I don't have the data from this point, but I have the results from our simulation, and now I have some confidence that this number is closer to that specific value. Finally, I conducted a three-dimensional simulation of the Bolund experiment. This experiment is conducted in the Bolund Hill located in Denmark, closer to the Riise University. And this hill, it's a small hill of 12 meters roughly, but it has all the characteristics for the validation and calibration of numerical CFD models. So with our new implementation, we are able to generate the surface of the terrain with a refinement capability closer to the hill. And for this case, I have a surface that is discretized with 175,000 grid points. And as I told you, it's refined closer to the terrain. If we see a cross section in this phase along the C direction, you can see as well a refinement capability. So you have better or smaller grid cells closer to the volume hill. In this case, I'm using 7 million grid points in total for the complete volume of the fluid domain. And for this simulation, I did a total of 180,000 time steps, and I average about 80,000 time steps as well. I have a logarithmic C profile water roughness of practically 0 because this is water. And the terrain has a no-slip boundary condition, so it's explicitly computed in here. These are the boundary conditions for the walls. So you have a velocity coming from the west and a pressure imposed outlet. As I mentioned, the velocity direction or the wind direction is coming from the west, and we are using the measurement points from the experiment of this line, which is the M7, M6, M3, and M8. So qualitatively speaking, we can see the velocity magnitude field from 2 and 5 meters above the ground level. In the top figures, you have the instantaneous time step, the last time step, and you can see all the complexity of the flow that is it's affected by the terrain. And in the bottom, you have the average results where you can see mainly 2 bubbles that are generated above the volume here. I selected a literature item from Schubiger et al. That was published last year to do some comparisons. In his work, he uses a conventional Lattice Boltzmann method, but he is using a regular grid, so he doesn't have refinement capabilities. So he has to conduct this simulation with 42 million grid points, which is about 6 times more the grid points that I've been using. And his simulator uses Smagorinsky turbulence model, which is less accurate than the one that I'm using, which is the Bremann's model. So you can see here, qualitatively speaking, that we have similar results, and we are capturing the complexity of the flow around the volume hill, and the average as well is behaving similarly to the results from Schubiger et al. If we check quantitatively, we can compute the speed up of the flow around the volume hill. So the speed up is how much the velocity or the speed is increased because of the shape of the volume hill. And you can see here for this 2 meters above the ground level that our model, which is the black line, is matching perfectly the results from the measurements of the experiment, and it's behaving better than the work of Schubiger. And even though that we have significantly less grid points because of the refinement capabilities. If we check the 5 meters above the ground level, we have similar results. We have 3 of them matching perfectly, and we have a difference behind the volume, behind the volume hill. But to be fair, we are in a location that is very tricky. We have a measurement point inside this bubble where we have a big gradient of velocity in here. Sorry. Oh. And in here, you can see that overall, the average error, it's significantly less if you compare to the simulation from Schubiger. And he also conducted 2 additional simulations in commercial software, such as ANSYS Fluent, and we still have better results if we compare to all 3 simulations. performance-wise, we use the same indicator of performance that Schubiger uses, which is the seconds elapsed per core per million cell. And in here, you can see that our model is compared with the three models, the performance of the three models. And since this indicator, if lower is better, we have a significantly better performance if we compare to all three simulations. This is because we have a smaller grid. We are retaining the same spatial accuracy, but with a smaller grid. We have much more computing power because we are using a GPU instead of a CPU. And we are able to conduct this simulation 9 times less if we compare to the Palabos Lattice Boltzmann method, which this is about 11 hours. And we conducted in about 1.2 hours, something like that. So significantly faster if we compare because of the refinement capabilities. That is why I'm telling you that even though we have this bottleneck of interpolation, we have the versatility to reduce the computational cost of the model because of the refinement capabilities. So just to wrap up this last section, we are successfully implemented the simulator for curved fluid domains, able to simulate low and high Reynolds numbers in 2-dimensional and 3-dimensional domains. It has the capability of local refinement with reduced memory allocation. The score is 34.6 times better if you compare to the work from Schubiger, from the specifically the Lattice Boltzmann method simulation. And as I told you, the interpolation stage must be reduced in the future. So it's something that I have in my mind. Finally, just to do a summary of all the achievements. So as I told you, for the first time, we did a GPU implementation of the Lattice Boltzmann method, 200 times faster than the HSLVM from 2018. The single-step Lattice Boltzmann method, it's 540 times faster than the HSLVM 2018. For the first time, we don't rely on the fractional step in the simplified Lattice Boltzmann method, and it doesn't rely on the interpolation stage as well. It is capable of simulating high turbulent flows, and it is capable to simulate in complex fluid domains. So all these features have been compared with the results from the literature, and it has been proven that our model is reliable for complex and realistic applications. The publications that I did during my PhD, there are 6 publications that I did during 4 years. 3 of them I'm the first author, and 3 of them I'm not the first author. And I intend to continue working on the single-step Lattice Boltzmann method, specifically in 3 articles in the short term. The first one is already finished, and I show you the results. And then I want to do a multi-patch connection of irregular grids to create even more complex fluid domains. And then a combination of hybrid regular and non-regular fluid domains to improve the performance of the models. And finally, in the mid-term, long-term, I want to package all this progress into a graphical user interface it will be dedicated for scientific research and also for educational purposes. And in the long term, or in 2023, I intend to add the interactivity with augmented and virtual reality. So basically, this is a brief summary of all the work that I've been done since 2017. And I hope that this is sufficient for me to get my PhD degree. And for that's all. Thank you all for your attention, and feel free to ask any question.